Hello, welcome to AP Calculus Lecture 3.4, where we're going to talk about concavity and inflection points. We're going to be looking at in a little while some of your homework problems on page 184, so you'll want to be open to that page. And you'll also want to have this note sheet printed out and have a highlighter available. So you're not going to have to draw anything. We're just going to go through the notes and I'll highlight the important parts. So what concave up means, it's just kind of it's a function that looks like this, where it's kind of looks like a bowl. So you just kind of have to memorize to the left of a point where you have an inflection point, or not an inflection point, but to the left, you're going from decreasing to increasing. That's a better way to put it. The function goes from decreasing to increasing, and you think of it as kind of a right side up bowl. For concave down, the function's going from increasing to decreasing. Okay, and it's just the opposite of concave up. So think of it kind of like an upside down bowl. So how do you determine concavity? So really what you want to do is think about the slope of the tangent line. Is it increasing or decreasing from left to right? If the slope of the tangent line is increasing from left to right, then the derivative must be increasing, because the derivative is just the slope of the tangent line. The sign of the slope doesn't matter, only whether it is increasing or decreasing from left to right. If a function's increasing, which is what you determine in the last homework, by taking the first derivative and doing the first derivative test, then its derivative must be positive. So let's take a look at my example here. See how the slope of the tangent line as you go from left to right, so although it's really negative, as you go around this bowl here, the slope of the tangent line actually gets more positive. So it's going from negative to positive. And by the time you get over here, it's really a positive slope, but it's a negative slope over here, but it's increasing from left to right. All right, so that tells you if the slope is increasing, the slope of the tangent line is increasing from left to right in terms of it's getting more positive, then it's concave up. On the other hand, if the slope of this tangent line as you go from left to right is decreasing, so maybe it starts off positive, but it's getting less and less, and finally it's going negative. So if the slope is decreasing from left to right, it's concave down. So curves are concave up when the second derivative is positive. F double prime of x is equal to 0. Curves are concave down when the second derivative is negative. An inflection point occurs where the second derivative is equal to 0. So where the first derivative is equal to 0, we had a critical point. That was a max or a min, usually, sometimes not, but a max or min. An inflection point is a place where the function changes concavity. So you can see on my example here, we have an inflection point right here because the function's concave up, still concave up, and then boom, when it hits an inflection point, it switches to concave down. Okay, so let's work. What we're going to do is kind of go back to yesterday's notes and work the same three problems again that were on yesterday's notes. I'm going to rehash what we did yesterday because on the homework you're going to have to do that. So our first example is we have f of x is equal to 4x squared plus 2x minus 2. So the first thing we want to do is take the first derivative. So that's going to be 8x plus 2. We're going to set that equal to 0 to find the critical point. And yesterday we found that the critical point occurred at x equals negative 1/4. Then we did a sine line next to the first derivative, put our critical point in there, and when you plug in negative 1, something less than negative 1/4, let's say negative 1, all right, we would end up with negative there. And let's say we plug in 0 because that's on the right side of negative 1/4, and we'd get a positive. So our function is decreasing until it hits that critical point and then increasing after that. And we had a minimum right there. So let's put down everything we know over here to the right. We're going to use all of this to draw a graph. So we have a critical point at x equals negative 1/4. We're decreasing from, we've got negative infinity, positive infinity, from negative infinity to negative 1/4. We're increasing from negative 1/4 to infinity. We don't have a max, but I want you to put that down, so no max. We had a minimum at negative 1/4, and then you have to plug in that negative 1/4. It might be easier to do it in decimal, but plug it into the original function to get the y value, and it was negative 9/4. So that's all the information that we had yesterday. We're going to have to do all this on the homework, so I wanted to remind you how to do that. Now we're going to get into the concavity part. So you take the second derivative. So let's look at this. That's just 8. It's the sign of the second derivative that matters. 8 is always greater than 0. So this function is always concave up. And I'm going to abbreviate that with the acronym CCU. So it's always concave up. There's no inflection point. So I'm going to write that down. Concave up from negative infinity to infinity, and that probably makes sense because this is a happy face parabola, right? The term in front of x squared is positive, so it's just a parabola. The inflection point, we're just going to write that in as none. So we've gained enough information here to do a rough sketch of the graph. And I'm going to want you to do this on some of your homework problems. So this is how you do it. First of all, let's start with the minimum. Negative 1/4, that's over to the left a bit, and negative 9/4, that's, you know, like a little bit more, a little bit less than negative 2. So let's just say that's about right here. We know it's always concave up. So our parabola would look something like this. All right, so we know the minimum's got to be the vertex of the parabola. I found roughly where that is on the graph. I know it's concave up. And so there you go. Okay, we're going to do this on our next two examples. We're going to do the exact same thing. Okay, our next example was g of x is equal to x cubed minus 3x squared minus 9x plus 1. First we do the first derivative test. We're going to have 3x squared minus 6x minus 9. We want to set that equal to 0. To make it easier to factor, I'm going to factor out a 3. And then we'll factor that trinomial so we can find where this derivative is equal to 0. So we had, I believe, x plus 3 and x minus 1. So our critical points occurred at x equal -3 and 1. Now I like to draw the sign line next to where I'm going to plug in. We had two critical points here. First -3 and then 1. So when we plugged in, let's see, I have this one backwards. Is it -1 and 3? Let's see, because that'd be giving, yeah, I'm so sorry. It'd be -3 and plus 1. So our critical points are at -1 and 3. Okay, that'd give me the -2x in the middle. So I apologize for that. Okay, -1 and 3. Okay, easy mistake to make. A lot of students make that. They get the signs backwards when they factor, and that messes up the whole problem. So don't do what I just did. All right. To the left of -1, when we plug it into the derivative, let's say you plug in -10, something like that, you get a positive number. You get a negative times a negative, so it's positive there. And then in between -1 and 3, let's plug in a 0. We'd get a negative times a positive, which is negative. And then greater than 3, it's a positive times a positive. And what we had yesterday was this. So I'm going to write down all our information over here. First of all, our critical points occur at x equals -1 and 3. We are increasing from -infinity to -1, and then again from 3 to infinity. We were decreasing from -1 to 3. We have a maximum at -1, and how do I get the y value? Do I plug it back into the derivative? No, you have to plug it back into the original equation. That maximum is -1, 6. And then we had a minimum at 3, and when you plug 3 into the original equation, you get -26. Okay, so we need to figure out now where is this graph concave up, concave down, and where do we have an inflection point. So we do the second derivative test. Now don't take the derivative of the factored version. Go back right back up to here, and the second derivative would be 6x minus 6. We're going to set that equal to 0. So if you set that equal to 0, x is equal to 1, and that is our inflection point, which I'm just going to call IP. All right, so our inflection point, I'm going to go ahead and write that down. It's at 1, and then we're going to plug 1 back into the original equation. So that would be 1 minus 3, that's -2, minus 9, that's -11, plus 1 would be -10. So at 1, -10, we have a change in concavity. Now I'm going to do a sign line for the second derivative. Put in our inflection point. A good number to the left of 1 would be 0. So 0 minus 6 is negative 6. So it's concave down. I like to just draw a concave down symbol there. Or you could write CCD if you want. And then to the right of 1, this whole thing would be positive. So after 1, it's concave up. You have to write all this down. Concave down from negative infinity to 1. And then concave up from 1 to infinity. So this is what you're going to be doing on your homework. All right, you're going to get all this information and list it at least for 3 problems. You're going to do this on 3 problems. You're also need to do a rough sketch of the graph without using your calculator. You won't get your graphing calculator on this test. So what I would suggest is plot the maximum. That's over 1 to the left and up 6. Let's say that's something like here. It doesn't have to be perfect. And then we have a minimum at 3, so over 3 and down 26. So let's say, I'm going to go ahead and write that negative 26, and this is positive 6. Also plot the inflection point. That is over 1 and down 10. That'd be something like here. Okay, we know to the left of our inflection point, it is concave down. We know that it's increasing until we get to negative 1 here. So the function is, you're going left to right, increasing, and then we hit the maximum up here at 6, negative 1, 6. Then it's decreasing, but it's still concave down. All right, we know it's decreasing between negative 1 all the way to here, but it's concave down until we get to 1, this point right here. Then it switches to concave up, and it decreases till we get to negative 26, and then starts increasing forever. So concave down from negative infinity to negative 1, to 1, increasing till we get to negative 1. So you just have to look at all these intervals. And then I tried to make it obvious that we switched, it's concave down, and then the bowl kind of switches to concave up there. All right, so then you can check it in your graphing calculator and see if you're on the right track at least. Your graph doesn't have to be perfect, but it does have to be correct in terms of where it's concave up, where it's concave down, where the maxes, mins, and inflection points are. Okay, let's do one last example, and then we'll talk about the homework. And our last example is the same as yesterday. We had h of x is equal to x to the 1/3. So we took our first derivative. That's 1/3 x to the minus 2/3. All right, that's going to be 1 over 3x to the 2/3. We know that can never be 0. However, we have a critical point where it's undefined at x equals 0. So I'm going to draw my sign line right next to that, because this is where I'm going to plug into. I don't like to plug into negative exponent. It confuses me. All right, we've got 0 here. To the left of 0, let's say negative 1, you're going to square that negative 1 and make it positive, so it's positive. To the right of 0, also positive. So you might remember from yesterday's example that we had this situation. All right, so all of our information We have a critical point at x equals 0. We don't have a maximum because it never starts coming down again. We don't have a minimum. We're increasing the entire time from negative infinity to infinity. And we never decrease, so I want you to write that down. Don't be lazy. Write it down. Okay, now let's do the second derivative to determine the concavity of this graph. All right, I'm going to take the derivative from this negative exponent. So that's negative 2/3 times 1/3. That'd be negative 2/9 x, and then negative 2/3 minus 3/3 to the negative 5/3. We're going to set that equal to 0. I'm going to make it a positive exponent so my brain doesn't hurt. I have negative 2 over 9x to the 5/3. Now again, this is never going to be 0, right? It's never going to be 0 because the top, same up here, can never be 0. However, you can have an inflection point where it's undefined, and that's at x equals 0. So we have just like the critical point, we have an inflection point at x equals 0 because it makes it this undefined. So we do our sign line for concavity. To the left of 0, let's say negative 1. Anytime you have odd exponents, it stays negative. So that's negative 2 over negative 9. If I plug in negative 1, negative over negative is positive. So to the left, it's concave up. To the right, it's negative over a positive, right? If I plug in a 1, I'm going to have a positive number on the bottom, so that's negative. And that would be concave down. So let's write down the intervals I know. We know we have an inflection point at 0. And I plug back to the original function. The y value is also 0. We are concave up from negative infinity to 0. And we are concave down from 0 to infinity. Okay, now let's make a sketch of this graph. We have an inflection point at 0, 0. There's no max or min, but I know it's increasing the whole time, so it's always going to be rising. And I know it is concave up until you get to 0, right? So it would look something like this. Increasing, still increasing. That is concave up, right? And then it switches to concave down. All right, so you can check that in your calculator, graph x to the 1/3, see if it looks something kind of like that. So let's talk about the homework. All right, the homework is on page 184. I want you to do 1, 2, 5, 21, 23, and 31, 63, and 64. Now, 1, 2, and 5, I'm going to show you these in a minute. Those are easy. They're just, excuse me, those are just graphs. And you're just going to give me intervals there. For 21, 23, and 31, this is what I want you to give me. Give me the critical point or points. Give me where the function is increasing, where the function is decreasing. Give me any maxes any mins, and if there's not one, state that. Give me the inflection point. Give me where it is concave up, where it's concave down, and sketch the graph. So for 3 problems, 21, 23, 31, you're giving me the entire business. Okay, we're going to add, next section, we're going to add asymptotes. But this is pretty much what your test is like, doing this stuff. Now, so 1, 2, and 5 are graphs that you just read. 63 and 64 are word problems where you're just finding minimums. So that's just the first derivative test. You don't have to do all that stuff. Just find the minimum. Okay, so again, 1, 3, and 5, you're just going to read the graph and tell me what intervals is it concave up, what intervals is it concave down. Then on 21, 23, 31, remember 31's trig, so you have to be careful there. You're going to give me the entire business, everything we did today. And then 63 and 64, you're just going to find a minimum, so that's just the first derivative test. You don't have to go through everything on those 2. All right, well, good luck on this homework. You can trust the answers in the back of the book. So for 21, 23, and 31, it probably just gives you a graph, and you'll have to read a graph for your answers. And if you struggle with that, then you'll just use the solutions video to see if you got them right. And then for the rest of them, you can trust the answer in the back of the book. No problem. All right, that's it for this video. I will talk to you next time.